Hello, welcome back. Today is lab day. I forgot to upload it until just now, but you can finish it anytime until Wednesday if you're seeing this later. So don't worry about it if you did miss it, which I think is a couple of you because there's some other stuff going on today. You will need the VM for this, so go ahead and start the long process of starting it. I'm going to use the browser-based one because I don't want to install their crapware on my computer. Actually, Horizon is pretty decent as far as VM softwares go, so don't feel like you can't install it on your computer. It's quite nice, and I don't know if they give you the premium version, but I think it's worth a couple bucks because you can do other operating systems on it usually. You'll also notice that with the lab today, there is a zip file. That's the code that you will need today. It's very similar to what we did in class. This lab and the corresponding code come from a different class, the old networks class from a couple of years ago, so basically unchanged. I think I didn't even bother changing the class number at the top. Turns out, not a lot of changes in TCP. Someone asked, anyone else's VM keep crashing? Yes, everybody's. Because it's a smoldering pile of crap. It really is, and I'm sorry, I wish I had another way to do this, but the only alternative is we just watch slideshows for 16 weeks because you can't do any networking on your own home network. Or you can, but then we'd need 25 IT people to help you through it. Someone said, I can't get on the VM, I just get a black screen. Sometimes it does that for a bit while the VM is like booting up or when the VM's very busy. It's connecting other people. And then you also get, if you've ever, instead of logging off, gone and tried to shut down your VM, I don't recommend that because it won't come back for about 10-15 minutes at least. The other funny thing you can do if you're really feeling like sabotaging yourself is, remember I told you not to do ipconfig-release? If you do, you will lose the VM for like, I don't know, I think actually you might lose it until you contact IT, but I know you'll lose it for at least like 20-30 minutes if you do ipconfig-release. I know this because of last time we did that lab in 428. Anyone successfully on the VM right now, since a few people are complaining that it's dead? Okay, I did see a couple of people say mine works, but a bunch of people saying that it doesn't too, so. Well, I will still go through it, and you can still write the answers down for these portions. If you can't finish this, you also don't need the VM, by the way. You could be, this requires you to pair up with somebody. You could be your own friend as long as you have two computers. So if you have a laptop and a desktop, or two laptops or something, you can run both ends of this. So that's your only escape from using the VM. And the code here that I've written for the sample is not that great. So just don't use it too much. It only handles one TCP connection for the TCP part. Man, VM's still dead for a lot of people. Well, typical. I think on the next exam, I'll just do a multiple choice test because this thing's too unreliable. Sorry. I don't think the practical was that enjoyed anyway, so we'll do a poll, but probably just do a multiple choice test. There we go. So is it just the not desktop versions that are working? Someone said it works if you use the browser. That's funny that the browser one is better. I'm gonna put a poll on the in-class. So thumbs up for working for you. I wouldn't be surprised if the browser one was more stable. I know that they've directed more of their attention to the browser one. The browser one is going to be the future here. It's already kind of set in stone. I'm going to go with the browser one eventually. Yeah, it's right up there as well. digitalworkspace.jcu. Let me see my poll results there. So it's still about 50-50. Cool. So a lot of people on, but not a lot of people on too. So I will still wait a bit here. Looks like I need to rename all my packages. Oh, it's so slow. Oh God. It's slow to the point that I have to slow down my typing. That's never a good thing. I don't know why bad computers take so long to rename packages in Eclipse. That seems to be one of the hardest things for them to do. Okay, so people are reporting that the browser version works. That is kind of funny. So I guess they were tinkering with it and they messed up the desktop one again. Invest in the... The problem is the CSVMs are only used by a handful of people, so they don't tend to see much investment. The VMs for everybody else are not so bad, the general VMs. But you can't do anything on them, so that's not really a huge testament to them. They're basically just a web browser. Can't really do much more. Well, you can use Excel in the regular one, I think, so that's a very business schooly thing. Alright, so it's the not UDP one that we're using today. And I've got the driver server and the driver client. So one of you will be the client and one of you will be the server. And one of you can pair up with me as well. So who wants dibs on me? We're gonna skip the UDP portion probably because we've already done it. We'll see. I haven't quite decided. Yeah, it's short actually. We'll keep it. All right, Nate's gonna be my buddy. Let's see. You can be the server, Nate. So you know what? No, I'll be the server because my IP is on the big screen. So The rest of you need to find your own friend. I got dibs on Nate. So that's my IP for you, Nate. 143.105.165.12. So one of you launches the server. You don't have to make any changes. The other one of you launches the client, and you have to change this IP in driver to your buddies. So I'm just doing this for demonstration purposes. This would be done on Nate's end. All I gotta do is go to the server here and run it. And wait. And wait. And wait. Okay. Mine's running. So as soon as Nate finishes typing my IP and launching it, we will connect. But before he does, I'm going to start my trace. And you should too. So before your client connects, preferably, start your trace. Before the other person connects, start your trace. You don't actually need to communicate once you've established the IP, so you can DM one another. Once you've picked a partner, just DM your IP to them. But you can sit in the chat channel too. You can make some more if we run out. Okay, and I'm going to start typing the Wireshark command while I get into this. So, you need your buddy's IP address, and you need your own IP address. So, Nate, you can DM me your IP. I'm going to start typing it with just some random one. So I want to get all of the messages where the source is me. One four three 105 165 12. The source is me, and the destination is my buddy's address, which I will find out soon. I'm just going to fill mine in there for now. And then I'll do an OR, and I'll copy this whole thing. I forgot some equals. So all of the messages where the source is me and the destination is my buddy's address, or vice versa. If you don't do the or vice versa, then you don't get all the messages coming back to you. Okay, so I got Nate's IP. We all have the same first three because we're on a /24 here, so you can just change that last number on one or the other here, doesn't matter. Okay, and so now I'm seeing all the traffic that comes in over this bad boy here, and looks like I typed one of these wrong here because I'm not seeing anything. 143 105 165 12. Six 547. Let's see. Why might I not be seeing it? So I am getting messages in my command line, in my console there, so I am getting those messages coming in. Oh, I want that. Okay, I'm an idiot. I had Wireshark open on my personal Wireshark instead of the VM. That would make a lot of sense. So IP source is your own, IP.destination is your buddy, and then or, and then the vice versa. Okay, now we've got to start over because obviously I missed all the original traffic, so I'm going to restart my server. Nate, you can restart your client, and we will get some new traffic here. Oopsie. Looks like I still got it running there. So I got my reset message when they tried to send me something without restarting his client. So it's not part of the lab, but remember you get the RST, the reset message. This, you know it's a reset because the flags are in the brackets here. It's a reset message when you get TCP traffic and there's no session. You get a reset message. So I sent a reset message back to his machine because the server died unexpectedly. Okay, so Nate connected. Now as soon as he connected, you see I got a bunch of traffic here. So I got it as soon as he connected. He didn't even have to send a message to me. And then when he sent the message, he sent a hello there. I got a bunch more traffic too. So now we can start looking at some flags and stuff. So let me move this over if I can. Yeah, that's going to have to do. And let's zoom in on this. Okay, so first, what is the window size of both machines? Client and server. And you can think of these in whichever way you want. I'm going to think of myself as the server here. So what is the window size and what MSS do both machines suggest, the maximum segment size? So where can we find that? That's going to be under our transmission control protocol details somewhere. Let's see, where can we find window size? There's window size for me. Now this one comes from me because this is the acknowledgement that I send. As the server, I send the second message. So my window size for the server is going to be the 65535. I'm just going to use the typewriter to complete this. You can have a separate document or however you want to do this. I forgot to include an editable one here. So mine is 65535, and then the client's a little smaller, so there was probably a little congestion there. His buffer is slightly busier than mine, but not by much. So 64240 on that end. Let's see if we can find the maximum segment size. That actually goes under options, so that's one of those extra things. You'll notice that there's quite a few here. There's 12 bytes of options. So you've got your standard 20-byte header, and then you've got your 32-byte header, because this is TCP, and then you've got your 12 extra bytes of options, so that gives you, over 40 bytes, 44 bytes total of header. It's a lot of overhead. In this case, my maximum segment size is 1460, the largest that you can fit into an Ethernet frame, right? 1460. So it's a number we'll see repeating quite often. This is the kind of standard maximum segment size. And let's see if the server has the same. So yes, both messages have the same maximum segment size. Now, during the handshake, one of the things that both of the machines have to agree upon is the maximum segment size. So let's see if these options continue, for example, during the payload messages when we send hello. You'll see that they are not there anymore. So many implementations of TCP do this. They exchange all of their options during the SYN and the SYN-ACK phase. So they will decide things like the maximum segment size and all this other different stuff here that we're not going to go into. The window scale is telling you basically what to multiply the window value number by. Of course, you only need to tell them that once. After they know what to multiply the window size value by, they'll just multiply it by that value for the remainder of the session. So in this case, the window scale is telling you to multiply this by 8. I believe Wireshark already does this for you. So the raw value that's been sent here on my end, if we look at it in the payload, is FF, 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 right? So just the maximum number you can get in this case, because it's 2 bytes and all Fs. And so Wireshark gives you this calculated window size, which I believe is the window scale times the number that you got. So I think what you get here is always the calculated value. And Wireshark will do this a lot, where it will just calculate things for you to make it easier for you to understand. We'll see that again pretty soon here with the sequence numbers. So we observe that the client sends data to me on 6112, and we can see that up here, that first message goes to 6112. I respond from 6112. We can also see that if we go back to transmission control protocol, we can see the destination port is 6112 on the original message, the SYN, and then the destination port is the source port on the original, and the source port is the destination on the original, so they flip. Okay, so the server is using 6112, and the client has chosen 64904. 64904, and it has done so because it's picked at random, right? It's just a randomly selected port. So when the client creates this session, they choose a port at random. So what flags does the first segment in the handshake have set? I'll let you guys answer this because this should be pretty obvious. I actually just answered it earlier. What flags does the first segment have set? What flags does the first segment have set this very first message from the client to the server? It's the first message in the TCP handshake. What flag do you set on that first message? Somebody said SYN and ACK. No. And then they corrected themselves to just SYN, and yes, they are correct. The very first segment in the handshake is just a SYN, right? This is set to indicate you want to establish a session. So you set the SYN flag on your first packet to indicate that you are interested in starting the handshake and establishing a session. Now in the second segment, already answered, right? It's SYN and ACK. So you can see that, again, Wireshark highlights those in brackets in the packet details because those are important, but you can also look in the body of the TCP info. There's a flags field where you can see all the different flags that have been set. So we can see things like urgent and push and reset and all that stuff here as well. So in the second message we have syn and ACK set. And this is acknowledging which is a hard word to spell. Acknowledging the request to establish a session. So this is basically confirming that a session will be established. Oh. That I shouldn't have typewriter 2 lines there, but that's okay. So we're acknowledging the request to establish a session and basically confirming the establishment of that session. So we keep the syn flag set to indicate that this is still part of the handshake, and then we set the ACK flag to acknowledge that we received a packet just now. The third segment should be the ACK, and this is the final part of the handshake, so it only has an ACK. Recall that we learned that this is the first segment that can carry a payload. So does it carry a payload? So this comes from the client, right? This is the last part of the handshake. Does it carry a payload? I'm going to let you guys answer that too. Does that first ACK carry a payload? And why does it not carry a payload? You'll also notice that from this point forward, all of the packets that we're going to see will have an ACK, most likely. That's going to be question 8. Something to observe at this point. But how does that one... Does it carry a payload? Why? Why not? To see, by the way, what it looks like with a payload, you can click on the one that obviously does have a payload. So this is the one that has hello in it. There's my hello. I think I'll just make this bigger. And we'll just go back and forth. Easier that way to see the whole screen. So, does the last part of the handshake carry a payload? Does the last part of the handshake carry a payload? So we have the syn ACK, and then remember this. And you see Wireshark also marks this in a different color to indicate that it's outside the handshake, although technically this is still considered the third part of the handshake. This is also the first load-bearing packet. You can actually send data here, but you'll notice that even if there isn't a payload available, hint, hint, it will still send this third part of the handshake. So it is still part of the handshake. It has to be sent out regardless of whether there's data ready to go. Whereas right now, even though there's no data going around, the session is still open here. So there is no payload. Someone is finally brave enough to say it. Yes, there is no payload here. And why? Why is there no payload? No need to send data, right? Because you haven't typed anything. So the only thing this application does is sends a string when you type something. So obviously, as soon as you've launched your client, you haven't typed anything. There's nothing to send. So it completes the handshake, but there's no data waiting. And this is true of many applications. The moment they establish the socket, they don't have any data to send into it. So in the overwhelming majority of applications, you won't see, well, I won't say the overwhelming majority, but most applications you won't see a payload on this end of handshake acknowledgement because you, the developer, when you implemented it, you don't have something immediately ready for transmission. You might think about how you would do this, but normally, let's say you're working in Java, you build the socket, then you do some stuff, and then you send some data in it. By the time your machine is done deciding what it's going to send, the socket should already be built, especially if it's a threaded application. So, generally you're not going to see data in this. That's not always true, and web applications, at least, will pretty much always send something here. So, for example, if you're connecting to a website, you also establish a TCP session, and you will almost always have some data in this third part of the handshake in that situation. Okay, so I'm going to stop typing out the answers to these. Encourage your listening. So the next one. Why does the third segment carry a sequence number of 1, even though the previous transmission carried no payload? And then keep this in mind later. So this third segment, the ACK-only one, we'll see it has a sequence number of 1. Okay, so the 1th byte. And we'll go back to, what does it say? The previous transmission carried no payload, so this guy here had a sequence number of 0. Okay, and we'll see the very first one had a sequence number of 0, so neither of these carried a payload. And then we have a sequence number of 1. So why did we go up by just 1? Weird, right? We'll also notice that the first one had an ACK of 0, and then we had an ACK of 1. And then we had an ACK of 1. Someone said each packet in the session has to have a unique sequence number. We'll see that the traffic from the server will continue to have a sequence number of 1. So the traffic from the server will continue to have a sequence number of 1. And the traffic from the client here forward, you can send me a couple more messages, Nate, so we can demonstrate this. The packets from the client, because in this implementation, the server never talks to the client, has nothing to send back. The messages from the client will always have an ACK of 1, because the server's never sent anything. There's some more messages, and we see that the ones from the server, so the ones originating from .12, on 6112, those always have a sequence number of 1 because we're not sending anything, and the ones that are coming back from the client, those always have an acknowledgement number of 1 because those aren't sending anything. So why did we increment it by 1 for the third part of the handshake there? Well, that's just convention. When we finish the handshake, we increase the sequence number by 1. Even if there's no payload, just how we do it. I don't know. It's a convention. So it's just an interesting thing to observe that we increase the sequence number by 1 after we finish the handshake. I'm sure there is a reason for it. I'm forgetting it now, but I think there's a good technical reason for it besides the fact that it's convention. I guess it's some sort of avoiding of ambiguity, but we increase the sequence number by 1 in the final message of the handshake. Why is the first segment the only one without its acknowledgement flag set? So the very first segment, that SYN segment, to establish the connection, doesn't have an acknowledgement flag. You'll notice all the other messages do. And that's a pretty straightforward reason. It's because we have nothing to acknowledge at that point. That's the very first segment in the session. So there is no previous packet from the server to acknowledge, and that is not true of all packets from that point forward. All packets from that point forward do need acknowledgement. So from that point forward, they all have an acknowledgement, but the very first one does not. That's why we have the ACK flag in the first place. Just for these very rare ones that don't have anything to acknowledge, like, of course, the very first one in the communication. There's nothing to acknowledge there. So although it has this convenient sequence number in Wireshark, the sequence number is actually set to a random value at the start of every TCP section. Wireshark just makes things a lot more convenient for us by starting it off at 0. So it just basically subtracts the random number of the first one from all of the ones in the rest of the session. So it gives you the raw sequence number here. That's the real sequence number, the randomly generated one. And then it just assumes that that is 0 and shows you what the rest would be, assuming that that was 0, and it was just simple subtraction. Okay, so how does Wireshark know which segment should be sequence number 0, the first one? Again, a pretty straightforward answer. It's the SYN, right? So the one that establishes the session, that one has the first sequence number. It has 35495891128 here. So the SYN is the first sequence number for the client, and the SYNAC is the first sequence number for the server. Notice they both pick their own random sequence number. So the client picked this sequence number, and then the server in its SYNAC response picked this sequence number, and Wireshark knows that those are the sequences for the client and server because they're contained in the SYN and the SYNAC messages. So Wireshark's able to follow this whole TCP session that way. And then in the future, you'll see the sequence numbers change, and the relative sequence number changes too, but those are very close, and we basically, again, pull those numbers from the SYN and the SYNAC, the relative numbers. Let's go here. So the sequence number raw here went to 129 from 128, just showing you again that it did go up by 1, and Wireshark is able to track that the relative sequence number, so relative to the first one being 0, is 1. Alright, so now it's time to send each other some data. You should have already done that, I guess, at this point, but you didn't have to. So now let's try a couple of other messages. So Nate, give these a shot. You've already sent a short phrase, so try sending a single letter, a longer phrase, and then something exceeding the maximum segment size. So it has to be larger than 1460 bytes. The best way is to just go type in your Eclipse console until it goes blank, because the Eclipse console can handle about 1500 bytes before it no longer can display it. You will have to hold down a key for a while. It'll take maybe 30 seconds of holding a key down or so before it actually goes blank. So be patient and send a very long message exceeding the maximum segment size. I'm going to find the short phrase first. Turns out it's hello, just like in the example. So here I've got my hello message. How many bytes is the payload? Count the bytes, or look at TCP segment length, or look at the payload size here. So lots of different ways to figure this out. You can look at data here, you can look at length here, you can count them, 1, 2, 3, 4, 5, 6 bytes. You can look, see if I can get it to display. It's going to be tough. I have to shrink some fields here. Okay, I don't need number. I don't need time. Uh-oh. Oh, I just sorted by number, didn't I? Okay. Looks fine. Looks like I just sorted by time. That's the default anyway, so I'm going to get rid of those. And there we go. Okay. You can see it. I've got length. It's the very last thing in the little summary window there, so you can also see it there. So you can see the length of the payload there, there, count them, or there. Quite a few different places to see it. It takes a long time to get Eclipse to go blank. You must have some patience to send the super long message. Nah, that's not long enough. 1500 bytes is a lot of characters. If a character is 1 byte, you're looking at 1500 characters. Takes a while to type 1500 characters. Alright. So 6 bytes was the answer for me. Might not be the answer for you. If you can include a snip here and just highlight, like circle the number of bytes, that's fine too. You don't always have to type this stuff. If you just snip and circle the relevant portion, that's good enough. What is the ACK number for the server's response to this segment? So when I get this message, how does the server respond in acknowledgement? It responds with a 7. So why is 7? I'll let you guys answer that. Why acknowledgement 7? So it was a 6 byte message. y x7. And we almost always talk in terms of relative ACK numbers because obviously these gigantic real ACK numbers are too hard to deal with. Like they're just too hard to think about. So we almost always use relative acknowledgements when we're talking about the ACK. So just remember that it's a randomly chosen number, but then don't think about that too much because it doesn't actually matter. It's a randomly chosen number, but we pretend that the first one is 0. So y is 7. What is ACK 7? We had a 6-byte payload here with a sequence number of 7 as well. So both the sequence number and the ACK are 7. How come? Let's see if I got my really big one. Ah, you didn't quite make it. Only 1163 bytes. Too small. Oh, this one looks like it cleared it. Oh yeah, okay. This is the same message. Actually, you cleared it by a lot. Looks like it broke into 3 parts there. Okay. Cool. So that's like 4,500 bytes. So, all right, no answer to why it's ACK 7. So, the ACK starts at 1. Once we're at the third part of the handshake, sequence number is 1. ACK is 1. Okay, so client sends a 6-byte payload. That means that the next byte that we are waiting for is byte 7. We've gotten 6 bytes so far. We are waiting for byte 7 next. So we send back ACK 7. It's as simple as that. So they sent 6 bytes to us. That means the server has received 6 bytes. So it ACKs 7. 7 is the next byte that it's waiting for. Remember, we acknowledge how many bytes we've received so far, not how many packets. So we've received 6. We ACK 7. Now let's look at the single character message. And then what is the ACK of the server's response to the single character? So let's see if I can find a single character message here. I got an A. And at the point that I get an A, the most recent ACK was 63 from the server. So at the point that I get an A, the session just before that, the segment just before that, indicates that the ACK was 63, which also matches the sequence number of the segment I just got. So when we get one character and the sequence number is 63, we ACK. Let me see if this is actually one character, by the way. Ah, it's not. It's one character with a space after it. So it's actually 2 characters, I think, right? Is this a 2-byte payload? Yep. Okay, it's a 2-byte payload. So anyway, the point still stands that we ACK 2 higher here. So if it was 1 character, we would have ACKed 64. But it was 2 characters here, so we would have ACKed 65. So if we've gotten 63 bytes, 62 bytes it would actually be so far, and then you sent 2 more, then we would ACK 65, the next byte that we are expecting. So the sequence number of that message, the single character message for me was 63. And then for me it was 2 characters long. For you it ought to be 1 character long. If it was 63 and 1 character, then we would have acknowledged 64. If it was 63 and 2 characters, then of course we acknowledge 65. Let's see if I lost it. Oh, I lost my TCP session, so I'm going to restart it. It probably just timed out because we weren't using it for so long. That's my guess. Why does every transmission from the client to the server also have the ACK flag set? What is the client acknowledging? So the server never sends anything to the client in this implementation, in my little Eclipse example. It's a one-way thing. So, in fact, that's why they're client and server and not two clients talking to each other. So, how come the client still has the ACK flag set in every message? Has the ACK flag set in every message, and it's always acknowledging 1, 1, 1, 1, 1. Because it's 1 is always the next byte that it's waiting for. So it doesn't know that it's not going to get anything. It sets the acknowledgement to 1 to indicate that it is still expecting 1 as the next byte. So what if the server side did suddenly decide to send something and it didn't show up? How would it know? It wouldn't know, and so it always piggybacks on the back of transmissions. It sends these acknowledgements even though nothing has been transmitted. So even when nothing gets transmitted, we still send acknowledgements in case something does get transmitted. There's no way to know. So even though there hasn't been any data received, we always send the acknowledgement indicating that we are still waiting for byte 1. By the way, going back to the question of how come we set the sequence and the ACK to 1 in the end of the handshake, right? Why we set the seek and the ACK to 1 at the end of the handshake, because we are expecting byte 1 first. The question is more like, why wasn't it 1 in the first place? Why do we start at 0 and then go to 1? It makes sense for it to be at 1. All right. Again, the question is, why do they always have the ACK flag set to acknowledge any potential data that's coming in, to say that we are still waiting for byte 1 as the first byte in the event that they do send anything, and we're also acknowledging their acknowledgements. We're indicating that we received their acknowledgements because the acknowledgements come in with no payload. We must have received them, or it's implied that we've received them, but that one much less than the others. We're acknowledging in case they send anything. We're showing the next number that we're waiting for. So now let's go on to the very long message that exceeded the maximum segment length. So the client might see some fragmentation. The server probably won't. So we'll see what you see. It depends on the implementation. This has changed each time I have done this lab. It's been a little bit different. It varies by different machines too. Some of you will have different results than others. So the first part of my very long message comes here. I'm looking for a message that has the maximum possible length, so a message with a 1460 payload. That'll be the first message, the first really long message in that really long transmission. So this one has a length of 1460. And what I'm looking for is push has been set to false. We'll see that this is the only received traffic where that's true. So these push always correspond with messages that I receive from the client. This is the first one where the push flag has not been set. I'm also looking for that fragmentation stuff that we learned about. So where's that at? Let's see. I've got some flags here. Nothing interesting there. I've got some bytes all around, but there's no fragmentation stuff. So even at the IP layer, let's look there. Oh, don't fragment. Okay, so these come in as whole IP datagrams. They come in as whole TCP segments. There's no fancy fragmentation going on here, or what is it? I'm not sure. What should I be looking for? Is there anything interesting here that I should be looking at besides the fact that the length is very high and the push flag isn't set? Well, we're out of time, so I'll just answer it. So we're looking for the fact that the push flag isn't set until we are done getting all of those messages. Now look, I get 2 messages, and then I acknowledge both of them with 1 ACK. So in this case, I didn't send an ACK for each one. I actually just sent 1 ACK for both of those guys. And then I get the final one from that series. So this is actually a 3-part message series. And then the push flag is set. And that tells the TCP implementation to push this data to the application. So all of that info sits in the buffer until it gets the push. And then it knows that it needs to reassemble all of these in order and push them to the application. So the push flag in this and most other TCP implementations tells you this is ready for the application. Basically push the buffer contents to the application. So it buffers these 2 1460 messages until it gets the last one with the push flag set, and then it passes the whole thing to the application. At that point, I would have received the message here in my console, but we had to restart. So also it would be too big for the console anyway. Alright, that's it for today. I think you should have all you need to finish it. If you just save your session, you should be able to see the rest. The only other thing you need to do before you and your buddies sign off is have them type exit on their client. The client should type exit, and then you can both see the disconnecting portion as well. So you can still just save this trace. You have to stop it first. So have the client type exit, and then both of you can stop the trace, save it, and you can finish all of this stuff offline. The UDP one I think you can do with just loopback, I want to say, so you can give that a shot with a loopback. Or again, use 2 computers or buddy up on it. The UDP one is relatively short. Okay, that's it for today. Feel free to sign off. I'm going to wait and see if I get this exit message. Everything looks okay there. So Nate, if you can send me the exit message, I'm going to observe it before I sign off. Make sure everything looks good. And have a little video record for everyone else so you can see what you're looking for in the exit message. So the Eclipse implementation that I've given you, when you type exit, it disconnects. Oh, so my session had expired here, so when Nate typed exit, it actually had to do the handshake again and reestablish the session. So you get one of these resets, means the session's expired. And then you see I got these fin, ACK, SYN messages here, and then there's some retransmissions. You can expect those to happen too. Resets and retransmissions after the session is closed. And here I'll have, this will have terminated. So you're looking for that fin-ACK, all the stuff that closes it at the end. So the fin-ACK, ACK. Fins, you're looking for fins. Okay, and then I stop this, save it, and I can use this later. Okay, thanks for tuning in, guys. Finish the rest of the lab by class on Wednesday, and then we'll go over the answers to the rest of the questions real quick on Wednesday. Have a good weekend, everybody.